Okay, good morning. um, Dr. Gunasegar, my presentation today is a hybrid neurogenetic causal conclusion based autoencoders for traffic prediction in smart cities. Good afternoon to everyone. So, my topic is how we are going to predict the traffic congestion in the urban cities or the small cities. In the modern era, the expansion of urbanization has led to the rapid growth of small cities. These cities leverage advanced technologies to enhance the quality of life for their residents by optimizing various aspects of urban living, including transportation. So, one of the most pressing challenges faced by the small cities is the efficient management of urban traffic control system. The escalating the rate of traffic congestion is not only result in the economic losses, but also the impact, the environment, and the overall well-being of citizens. To address these challenges, accurate traffic prediction models are imperative to enable the productive traffic management and alleviate congestions. The problem statement of this study is the traditional traffic prediction model often falls short in capturing the complexities of urban traffic patterns due to the inability of account for nonlinear relationships, temporal dependencies, and evolving the traffic conditions. The advent of smart cities has introduced the new dimension of data such as real-time sensor and GPS traces and social media inputs, which necessitate more sophisticated techniques for accurate predictions. Consequently, there is a growing need for the new approaches that can leverage these diverse data sources and effectively predict the traffic patterns. The objective of the research is to develop an advanced traffic prediction model tailored to the intricacies of smart cities, aim to design the predictive framework that utilize the hybrid neurogenetic causal convolution based autoencoder, and this model should consider the dynamic nature of urban traffic data and incorporating the temporal relationship and the diverse data sources to achieve improved predictive performance. Previous studies of this research, a deep enforcement learning framework for controlling the autonomous vehicles in congested the traffic scenarios is introduced in the previous author. The authors demonstrated the effectiveness of using deep neural to learn the traffic patterns and make the real-time driving decisions, and highlighted this AI-driven traffic management system in the smart cities. Predicting the urban traffic flow using the deep learning approach is developed in the previous studies. The authors utilized the convolutional and recurrent neural networks to capture the spatial and temporal dependencies. Thus, research showcases the feasibility of deep learning models in enhancing the traffic prediction accuracy. The applications of big data architecture and management learning algorithms in the healthcare field that shares the similarity with the smart cities is found in their studies. The survey highlights the importance of data-driven approaches in complex domains and discussions in various techniques for handling and analyzing the large data sets. Bike sharing system within urban environment. This research implies the deep learning techniques to predict the bike demand in the studies. Also, there is another study in the long short-term memory networks for predicting the traffic congestion in smart cities by considering the traffic data from various sources. So, including that sensors and GPS traces. The authors demonstrate the potential long short-term memory networks in providing the accurate and timely conjunction predictions. The research methodology, the neurogenetic optimization, is obtained that focuses on enhancing the architecture of the autoencoder. The autoencoder is a type of neural network used for dimensionality reduction and feature learning. So, neurogenetic optimization techniques are applied to automatically design the architecture of the autoencoder. The genetic algorithms, which mimic the process of neural selections, are utilized to evolve to fine-tune the neural network structures. This optimization ensures that the autoencoder architecture is well suited for capturing the relevant features from the input data. So this is a genetic algorithm, how it is worked. There are 5 different steps. One is the population, another one fitness function, selection, crossover, and mutation. So the experimental setup evaluation is the data pre-process, preparation with the pre-process, training 75%, 70%, testing 20%, and validation 10%. To subset the assess the model of performance on both known and unseen data. Then evaluation metrics used root mean square error, mean absolute error, and squared scores. Then hyperparameter tuning is carefully select and tune the hyperparameters of the HNG and CCA models, including the training rate, batch size, the number of epochs, and genetic algorithm parameters to optimize the predictive capabilities. So the resultant discussions, we can see here the hyperparameters values, the learning rate, batch size, the number of epochs, optimizer, filter sizes, the number of layers, numerous per layers, and poolings, activation functions, dropout rate, genetic algorithms, population size, generations, crossover probability, mutation probability, and mutation strength. Here we can see the results of accuracy and root mean square values, then means absolute errors, then R square scores of different LSTM, DAG, and the proposed method of HMC and CCA methods. So the contribution and potential impact of this model, the integration of neurotic genetic optimizations and the causal convolution autoencoders in the proposed model represent the novel contribution to the field of traffic prediction. The enhanced predictive model capabilities, this model is support the superior performance in terms of accuracy, error reduction, and model fit, highlighting the effectiveness of providing accurate and reliability data predictions in smart city application. Then practical applications, the outcome of this research to produce the enhanced traffic management strategies in the smart cities, leading to improved traffic flow, reduced congestions, and more sustainable urban environments. So the conclusion of the study is to present a hybrid neurogenetic causal convolution based autoencoder approach for precise traffic forecasting in dynamic smart city environment. By combining this neurogenetic optimization and causal convolutional autoencoder, it tackles the urban traffic complexities and temporal dependencies. While fictional experimental results highlight this proposed model superiority over baseline methods, showcasing the enhanced prediction accuracy. So this proposed model consistently outperformed the baseline in accuracy matrices, promising the practical application in smart city traffic management for informed decision making and efficient urban planning. So these are the research references we used in this research. Then thank you very much for that. If there is any question to answer, we are happy to share with you.